Hello, this will be a demonstration of proposition 10 from book 2 of Euclid's Elements, which states that if a straight line be bisected and a straight line be added to it in a straight line, the square on the whole plus the added straight line plus the square on the added straight line are double of the square on the half and double of the square on the half plus the added straight line. So let's start by drawing everything out. We have a straight line, AB, and point C on it, such that AC equals CB. This is what it means for a point to bisect a straight line. And then we shall have a straight line of arbitrary length, BD, added to AB in a straight line. And what we are going to prove is that the square on AD, which is the whole is AB, the square on the whole plus the added straight line, AD, so the square on AD, plus the square on the added straight line, that's BD, so square on AD plus the square on BD, equal double the square on the half, in this case it'll be AC, so double the square on AC, plus double the square on the half plus the added straight line, that will be CD here, and so and final, what we have to prove is that AD squared plus BD squared equals double AC squared plus double CD squared. So let's get by drawing everything out. First thing we shall do is from the point C, we shall draw the straight line EC perpendicular to AB. We can do this by proposition 111. And furthermore, we shall make EC equal to AC or CB. Doesn't matter which one we make them equal to because AC and CB are equal to each other. We can do that by proposition 1.3. I believe I forgot to write. I did. It's unfortunate. Next, we shall simply join the straight lines EB and EA. I drew them in the reverse order though. And we can do that by postulate 1. We've been doing this since literally the first proposition. Next, using proposition 131, through point E, we shall make the straight line EF parallel to AD, and furthermore, through point D, we shall make the straight line DF parallel to EC, like so. Right. So that's the first part of the construction we're going to do. Unlike every other proposition in this book, the construction is going to be spread out through a few steps. So I guess that's a nice change of pace. But the step we're about to go through is very important. So we know that the angle CEF plus the angle EFD equal two right angles. We know this because they're the co-interior angles of parallel lines, namely CE and DF, and so their sum should be two right angles. We also know that the angle BEF, being a part of the whole angle CEF, must be less than angle CEF. We can then say by a property of magnitudes that the angle BEF plus the angle EFD must be less than two right angles. We also know by the fifth postulate that if co-interior angles are less than two right angles, the straight lines, if produced indefinitely, will at some point meet. And so if we produce the straight lines EB and the straight line FD in the direction of the points B and D, the straight lines EB and FD will meet. And say that again by the fifth postulate. So let us produce them using the second postulate to such a point, let's call it G, and then we shall join again by the first postulate, we shall join the straight line GA. And now we are actually done with our construction. Now, because AC equals CE, we know this because we made them that way, we can say the angles which they subtend are also equal by a proposition 1.5, and so we can say that the angle EAC equals the angle AEC. We also know that the angle at C is a right angle, again, because we made it that way. We made CE perpendicular to AB. And so we can say, again, by another property of magnitudes, that EAC and the angle AEC must each be half of a right angle. This simply makes sense. We know that the sum of all the three interior angles of a triangle must add up to two right angles, And so if one of them be a right angle, then the other two have to add up to a right angle. And the only way for them to add up to a right angle and for each angle to be equal is if each is half of a right angle. And so that is how we can say that the angle EAC is equal to the angle AEC. Similarly, we can prove that the angle CEB and the angle EBC are also half of a right angle, because we know that CB is equal to CE, and so we can say that these angles are equal. And again, by the same reasoning as the last time, we know that because all three of the angles have to add up to two right angles, one of them being a right angle, the other two have to add up to a right angle, and if they're equal, the only way that can work out is if they're each half of a right angle. And so we can also say that the angles CEB and the angle EBC are also half of a right angle. And if we add two halves of a right angle up together, well, we must get a full right angle. And so if we add the angle AEC, which is half a right angle, with the angle CEB, which is also half a right angle, we know that the full angle, namely AEB, must be a right angle because it's the sum of two halves of a right angle. And two halves is simply just one. And that step, so now we know that the angle EBC is half of a right angle. We just proved that. And so we can say that its vertical angle, namely DBG, is also equal to a right angle. We know this by proposition 115, that vertical angles are equal. We can also say that the angle BDG, being an alternate angle to the angle at C, will also be a right angle. We know that the angle at C is a right angle. We made it that way. And because we made EC and FG parallel, we made EC and DF parallel. And if we continue producing DF, the lines will still be parallel. And so we can just say that CE and FG are parallel. And if we know that they're parallel, then we know that the alternate angles, which are created by a third straight line following upon the two, must also be equal. And so we can say that the angle ECB is equal to the angle BDG. We know that the angle ECB simply is a right angle, and so we can say that whatever it is equal to, namely BDG, must also be a right angle. And in this triangle BDG, we have a full right angle, we have half of a right angle, so the remaining angle, namely DGB, must also be half of a right angle. And because DBG and BGD are both equal to half a right angle, they're equal to each other. And so we can say that the straight lines which subtend them are also equal by proposition 1.6. And in this case, it shall be that BD and DG are equal. Not in the exact same way, but we're going to prove a similar thing. We know that the angle EGF is equal to half a right angle. We just proved that in the previous fifth step. We also know that the angle at F must also be a right angle. How we know this is because in this whole parallelogram ECDF, simply ED, we know that alternate angles have to be equal. This is by weird shadow. We know that alternate angles in a parallelogram also have to be equal. And so if one of the angles is a right angle, we know that its opposite has to be a right angle. And in this case, we do. We know that the angle at C is a right angle, again, because we made it that way in the first step. And so we can say that its opposite, the angle at F, is also a right angle. So again, in the triangle EGF, we have three angles such that one of them is a right angle, a second is equal to half a right angle, and so the remaining angle, to make the whole thing add up to two right angles, must then be another half a right angle. And so we can say that the angle GEF is also half of a right angle. And the angle FEG, being a half a right angle, and the angle EGF also being half a right angle, we can say that the two are equal to each other. And so that the straight lines subtending them, namely EF and FG, are also equal, again by proposition 1.6. Oh. We're moving on to the second phase of this, I suppose. We know that not the angle, oh mercy, I've been doing this for too long. It's been like less than 10 minutes though. We know that EC and AC are equal to each other. We made them that way in the first step. And so we can say that the squares on them are also equal. This is a property of magnitudes. And if they're equal, then we can also say that the square on EC squared plus the square on AC squared equal double the square on AC. This is all to say that because EC squared equals AC squared, we can say that EC squared plus AC squared equals double AC squared. This is another form of common notion too. We're adding the square on AC to both sides of this. Yep. That. I was pointing at the wrong step. Okay, we also know that EC squared plus AC squared also equals EA squared. This is by the Pythagorean Theorem. So if we look at the triangle going on here, we're talking about this straight line and this straight line, which evidently contain a right angle. And so the square on the side subtending the right angle, in this case EA, must equal the sum of the two squares on the straight lines adjoining the right angle, or containing the right angle. And so we can say that EA squared equals EC squared plus AC squared. And by common notion 1, we can say that this EA squared is equal to double the square on AC squared, for both are equal to EC squared and AC squared. Similarly, we can prove that the square on EG squared equals double the square on EF squared. How we go about this is similar. So we know that EF and FG are equal. We proved that in step 6. And if they're equal, then the squares on them must be equal, again, by a property of magnitudes. And so we can say that EF squared plus FG squared equals double the square on EF. And we also know that the triangle EFG is a right angled triangle. And so we can say that EG squared is also equal to EF squared plus FG squared. And so we can furthermore say that EG squared equals double the square on EF. We also know that EF is equal to CD. We know this because they're opposite sides in a parallelogram. That's a proposition 134. And so by a property of magnitudes, we can swap out EF for CD and say that and we can say that EG squared also equals double the square on CD. And if we add the results of step 7 and step 9 together, we can reach that AE squared plus EG squared equals double the square on AC plus double the square on CD. Mercy. That's just common notion too. Adding equals to equals. Okay. We also know that AE squared plus EG squared must equal AG squared. Again, we're dealing with another right angle triangle. In this case, it's the triangle EAG. And so we can say that the square on AG equals the sum of the squares on EA and EG. And so we can say that AG squared is also equal to double the square, double AC squared plus double CD squared, because both are equal to the same thing, namely AE squared plus EG squared. It's just common notion 1 again. Prop 147 and common notion 1 again. We also know that AG squared is the subtending side of another right triangle. We know that it's the side subtending the right angle in the triangle ADG. And so we can say that AG squared is also equal to AD squared plus DG squared. We also know from step 5 that DG is equal to DB. And so we can also say that AG squared equals AD squared plus, swapping out GD for BD, AD squared plus BD squared. And so we can, again, by common notion 1, say that AD squared plus BD squared equals double the square on AC plus double the square on CD, for both are equal to the same thing, AG squared. And this final conclusion being what was set out to have been proven right up here, we're done with the proposition, therefore, etc., QED. Again, I don't have much to say about this proposition, much like the last one. So I will simply end the video here and move on to Prop 2.11.